Actually, this is a project we are currently doing for New Jersey Department of Transportation. And I would actually want to finish quick, so get some of your wisdom. Our primary thing is the testing. If there are a lot of quotes coming in, how do I evaluate it? That's our primary mission. First couple of slides I borrowed from Geraldo. This is again, I want to emphasize this overcoating. It's not the first one. So only we do very small part of the bridges or other structures. And this is before, and this is after. You can see the green overcoating. And as I said earlier, right, primarily how do we approve new products? And we are essentially going by the previous approved projects. Now NJDOT is going to have their own criteria instead of using the New England consortium thing. And we are supposed to develop both the test method and also the acceptance criteria. And also a little bit of quality assurance. Essentially, we get a signature of all these coatings. So after it's approved over the years, they can just make sure that's what they're getting. My colleague, Professor Hussam Najim, will present that part of it. And overview of a project, the current, right, approved coatings, NJDOT. Actually, when we wrote a proposal, they had only 2. Now, I think they have 6. And they essentially took from NEPCOAT, but now they're not doing that one anymore. And we did a lot of literature search, and we looked at all the 50 states, what they're doing, and new versus overcoating. And as you could imagine, right, said, yeah, coating is coating, what's the difference? But I think there is a little bit difference, especially for testing. I'm going to go through that one. We found only like 3 or 4 states really distinguish. Otherwise, it's approved for one, just use it for the other. Don't bother with too many things. Okay? And the other one, as I said, right, we want to develop methods to simulate field conditions. And also the reduction of complexity. Those 3 bullets, right, it's kind of intriguing me, even after 50 years of concrete research, right? You go through all the tests, they do it sometimes for 5 years, 6 years, and essentially they come back and say, well, I can't really figure out what is what. And one conclusion, right, nothing is good for 100 years, we know that one. And this one went through 1 millimeter. Just to measure creep of 1 millimeter of rust, it takes 5 years. It's kind of, I was not too happy about that one. And also, what it does, it prevents the competition. So unless you have a few $100,000, probably $1 million, you can't even get to it. So then only few companies can afford to go through this process. But eventually what happens, it also stops the innovation. New people coming in say, no, this is too much for me. Okay? So that was our thing. Now, going back to the overcoating, right? Essentially, I'm sure you know more than I do, it happens at the joints and support systems where the salt water goes in and it just does all kinds of degradation. And the typical scientists, for example, we always worry about UV. So we just go by the science, right? For this one, it's not. The primary thing is the salt, and it comes repeatedly, and also erodes and crystallizes, and that's only that part of it. And then, even I'm sure most of you do too, that you look at the bridge, yeah, I'm going to do the whole bridge. I think they're just doing it, one of our bridges here. But if you do this one early on, you can do it probably 1/10 or 1/100 if you catch it early, and you do only small parts of it. And it's soaked with chemically contaminated water. And since they're not exposed, right, you have longer drying periods. And also repeated soaking increases salt concentration. And then the abrasion, right, comes from all these little guys going through these things. And other important thing, right, it's a lot more difficult to clean. I'm sure some of you worked in the field, right? I did have a few chances. One thing is to sit down and write all the specs. The other thing is to really do it. You go there is no space, there's bolts coming everywhere. So yeah, they're going to clean and go. And that's another problem. And then primary degradation mechanism is creeping from existing corroded surfaces. Essentially damages, or when they have all these bolts and everything, right, they just slap the thing in there and it just comes off, and then it goes there. So that is a primary mechanism. It's a salt and creeping. And that's what we focused on, coming up with a test method. This is why it's different from the regular one. If you got the regular bridge, they do have some UV. And because I don't want to go too long, just want to jump on, we decided to prepare samples, right, which is pretty similar to the girders we use. So we took L sections, 2 inch by 2 inch, and then to simulate what happens in the supports, we put holes, bolts. Also put a couple of lines of weld. Some of you might know around weld, right? You get more corrosion. And the surfaces we want to prepare using handheld small tools, not a big one. Okay, the next one, the last bullet, this one is one of the things actually I need your wisdom. Some of you have gone through, right, the classical testing. You coat the surface and you cut it, X, to create a damage, and then you see how that thing grows. And that's after, as I said earlier, right, after even 5 years, you get 1 millimeter and it's very difficult to measure. So we wanted to expand that area surface. And we had all kinds of meetings and this and that with my students. So we decided we are going to put a circle. And the thing is, once you put a circle, that part gets isolated. And the creep goes everywhere. So I can get it much faster. So I don't want to wait 5 years. Our aim was to get this thing done by 6 months. I should have enough. And I should have sufficient information quantitatively. I don't want to look at millimeters. Those are the two things. So I said, okay, this circle will push it through. The second one we found is, I think there is a researcher from England, UK, said if you freeze it, the growth becomes much faster. So we used those two combinations. And I will show you, I think it actually scared me where it just goes on too fast. So those are the two things. We put a O-ring, and then we do the freezing also. Those are the two key differences. So to get this thing, what we do is we take this little ring, and you use a water-soluble glue, and put it on these things. And then we spray the epoxy mastic, whatever the DOT coatings, we pick like 2 or 3 of them. And then after this thing is dried, we just pull it out. And the last one, if you do this, where is my, yeah, here it is. The last bullet, right? After the coating is cured, we remove the O-rings, leaving approximately 3 millimeter of exposed steel around 20 millimeter circles. And those circles are the ones simulate the damage. And here again, top 2 is you can see the L sections, and this one, you can see the rings in there, and this one you can see pulled out. Right? And then for spraying again, remember we are dealing with a very small area. What we found is low pressure, low volume works very well. Because again, a confined area, it doesn't drop out, it doesn't spray everywhere, very little rebound, and we could get 70 to 100 micron thickness, very uniformly, without too much trouble. And we also went through like 5 or 6 different machines, and we settled on this one. And actually, it can cover large areas without much problem. And the right side, you can see this, assemble the things line by line, and they spray the thing. And then we check the thickness, as I said, right? So it can get pretty uniform. And we are professionals, but we are not real professionals in spray painting. But we could do it pretty good, the students. And this one, I'm not really sure. I want to tell you all these details. I just want to keep it 1, 2, 3. And you can see the angle, right? With the bolt hole and those rings. We built our own plastic tank, about 150 gallons. And we pretty much follow the 3 or 4 ASTM standards. How to build it, how much they should be apart. We follow the ASTM standards. And then we also wanted to have some UV, so we put the heat lamps and ultraviolet lamps. And the third bullet is the important thing. We added it. So we had a deep freezer. It goes to 0 degrees F. And it stays there in the night for 8 hours. And that really creates a lot of damage. And again, the last bullet, I want to say again, the primary mechanism is the creep of rust through the damaged parts rather than the UV. Okay, the cycling, primarily wetting and drying. And we went and picked up the salt from NJDOT, whatever they use. This is one place where we did not follow ASTM, so we are going to use whatever they are going to use, and 5%. Again, remember, we do it repeatedly, right? The concentration increases. And it goes through 16 cycles, right? Wetting and drying. And in the night, we put them in the freezer. So we call them, the whole thing is a big cycle, large cycle. Master cycle, right? Call them 24 hours. And after each master cycle, we clean the solution and rotate the specimens. These are all ASTM standards. And after every 14 days or 14 master cycles, we pull the thing out. So just perfect adhesion tensile strength. That's the last bullet, right? Pull-off testing. That's also an ASTM. This is the tank, see the pump and all that. And this one also, as you know, right, we are getting a grant and try to buy a tank, you want $100,000. I said, I don't have that kind of money. So this is pretty economical. So you just glue the thing and just pull it out. And you could see the 20 millimeter things. You can see this one, right? Just goes right on the top. And the dollies are glued. And this little thing holds at the dolly. And it pulls it out. And everything is instrumented. It tells you how many PSI. As you could imagine, right? It's around 1,000 PSI to begin with. And it keeps going down. And as the thing creeps, we get the pressure. See, now I get a big number. In the beginning, I got 900, 800 PSI. After 14 cycles, I go to 400 or 600. I don't have to worry about measuring, cleaning, and all that stuff. And I get a big difference. So that's much easier to quantify. And here you can see when you pulled out 0 cycle, right? Nice and clean. And as you go further and further, right? 14 cycles, 28 cycles, 42 cycles, you can see the corrosion here. Again, as I mentioned, right, these guys go from everywhere. And again, I'm not measuring the thing, I just want to pull out. And then we are going to analyze those things, as my student says, analyze it to death to find something, which we can do it repeatedly. And we can get something in 6 months. I think we're almost there, hopefully. And this is where I need your wisdom. If you don't like something, I really want to hear from you. What's wrong with this thing? And you can see these numbers going down for the 2 sets. The top one, you can see it started at 800. You have 3 points. See how fast it's stopping. And fortunately, these systems, right, we know in the field they did not perform well. So we purposely picked that one to make sure our system works. Now our challenge is to get the best one, to hope that 800 will not go below 600, especially in the beginning. And that's it. As I said, this is still ongoing research. We have just finished this one. And I was telling my students, this is just too good to be true. I said, we are looking for 800, 700, 750, something like that, but it just goes. Yeah. As I said, right, the new system does provide quantitatively measurable response variables. And we are going to continue this one. And we want to establish the repeatability testing, right, 3 more sets to make sure it doesn't go all over the place. And we are also looking for the best one to bring that thing. And then in terms of analysis, right, we love it, right? So we have those different points. We can do slope. We can also go into measure how much it creeped. Because there are two degradation mechanisms. First, we lost area, the 20 millimeter, right, probably became 14 millimeters. But even within that 14 millimeter, right, maybe it's weaker. So you want to establish what goes on there. And we also like to correlate to field performance. Fortunately, I think Matthew Bridge, correct me if I'm wrong, New Jersey did 20-year study. And I actually wanted to do 40-year study. He said, no, Dr. Bala, it's been overcoated already. They finished, cleaned, and coated it again. So they did at least 25 coatings. So we are trying to get some correlation from the field. And I'm sure some of you read the ASTM, right? They tell you right in the beginning, there's no correlation. It's only for comparison. Repeatedly, right, they tell you. But we want to have some kind of a correlation to study the thing. As I said, we can compute the load, contact area, and the number of cycles needed, and change of slope as we go further and further. We could also use the slope to get some other data, right? We want to find the thing and the field performance, yeah? And then we go back to our paperwork. We pretty much like to follow as much as NJDOT does now. And the NEPCOAT, NJDOT essentially, right, was following the NEPCOAT. So we are just going to use the same procedure. And essentially, if a company wants to bring a coating to NJDOT, they will do the tests by certified agencies, and they'll give the numbers, and then NJDOT will accept or not accept.
So like Dr. Balaguru mentioned that part of this project also is to do quality assurance and signature of these overcoating systems. So we are doing on this project actually something we call the IR scan or infrared scan for these overcoating systems to help really with the quality assurance and the acceptance when you are accepting samples from the construction site. So actually what we are doing, we're gonna actually test samples from the manufacturer. So actually we're gonna get several batches from the manufacturer and then establish baseline criteria for correlation. And then every time you have a sample that you really want to test whether it's acceptable or not, you can use this, you can use these correlation coefficients for these particular paints. The IR scan is actually a very well-known technique. It's used for many other products, pharmaceutical, for medication, for many things, almost like fingerprinting. So actually, these are the type of paints that we have tested so far. This is like, it's an ongoing project. I just want to show a couple of samples of these. So really to establish a reliable correlation, actually, like I said, 3 batches looks like to be enough. We have done that actually previously for another project on concrete admixtures, which are really much more involved to do IR scan for concrete admixture. It takes actually longer time, and you have to do several processes to prepare the samples. Actually, steel paints is relatively easier to do. So we're actually doing 3 batches. So you have to get from the manufacturer excellent samples so that you can establish the baseline. So you scan 2 samples from each batch. You get a total of 6. I think that should be enough to establish a reliable correlation factor. So this is really a typical IR scan for a paint sample. You measure basically percentage of absorption versus wave number, which is standard technique. And like I said, this becomes like a fingerprint of that particular product you can compare against. This one actually shows two samples from the same batch. So they should be very similar because they are really the same. So what we gonna do, actually gonna have 4 more. So 2 more batches, 2 different samples from each batch. So we're gonna have total of 6. This actually I'm showing from previous project. So when you have 6 samples, actually they're almost identical, and the correlation factor actually becomes really, really high, very close to 1. This one actually may be difficult to see, but like doing it for previous paints, not really the overcoating system for this particular project, but from previous project what we did, these factors are very close to 1, so 0.998, 0.99. So actually when you, the procedure actually is statistical analysis, how to establish the correlation. So you take the mean, and then you do the correlation for each particular sample out of the 6 samples. And then you either average them, or you do a weighted correlation factor. And if the correlation factor actually is very close to 1, which is the case with the steel paints, 0.998, 0.996, actually what you need to really get more reliable values, actually you have to do something called Fisher R to Z transformation, which is really a statistical method to do that. You go with these values, Z factor and standard error, and then you do the mean value of the Z value, and then you come up with a weighted mean correlation coefficient. And actually going back to this, actually this one is the R average, so I'm just gonna skip this one. So you're gonna have to do this really when these R values are close to 1. And I think this is probably the last slide. We haven't really tested any samples from the field yet because we haven't established the correlation factors. We are still waiting on the last batch to have all the 6 samples. But the ones we did for concrete in 2011, basically we had arithmetic mean and we had the weighted mean just to compare really if we use which one. So what we did, we took from the field a sample, we did 3 scans of that sample from construction project, and we tried to see if it passes or fails versus the established correlation coefficient. So, we just wanted to see using the arithmetic mean versus using the weighted mean. So, while some of them fail using one correlation, the other ones pass. And actually, we did 3 samples from the same product, okay? We're actually talking to the NJDOT about okay, you get 2 of them pass, so probably we'll let it pass. So actually what we're gonna do is gonna do something similar. So we're gonna establish, and for the steel paints, definitely we're gonna use the weighted average, the weighted mean correlation, because the correlation factor is very close to 1. And then we're gonna basically give this information to NJDOT to have a quantitative method of accepting or rejecting construction field samples. So that's actually what I wanted to talk about in terms of quality assurance and signature. And actually one thing I want to mention here is that every time you get a new product, you really have to, let's say if the manufacturer has changed their chemistry or their chemical compound, you really have to establish a new correlation coefficient as well.
Thank you very much. The preceding video was produced by the National Center for Pavement Preservation. More information can be found at tsp2.org. That's tsp2.org. Additional support provided by Michigan State University.